Okay, Mr. Smith here, and we're solving for three different equations for the sum of the forces in the x direction, the sum of the forces in the y direction, and the sum of the torques. And we're just making equations based on the variables that were given in the problem. If you haven't read this problem, just go back to the website and read that quick so you have just kind of the gist of what's going on. But basically, we're just making these equations. So I've taking the liberty of drawing in these forces and kind of making these to make this work a little bit quicker. If you're doing a problem like this on your own, you definitely want to go through these steps. So I've got the force of gravity from the sine here at the end pulling down. I put a little arrow for that force of gravity. I've got the tension from the cable at this angle, and I break that into its components. So T cosine theta and T sine theta. The mass of the beam is right at the center of the beam. Remember, any object that's going to be rotating, in this case, the beam is what would be rotating. We can draw its force of gravity right at the center of mass of that object. So I've got this mgb right at the center of this beam, and I've got the forces from the hinge, really be just this one force that kind of breaks into components. And we've got those components here. That's the force of the hinge in the x direction and the force from the hinge in the y direction. Okay, so let's just start making the equation. So the sum of the forces in the x direction equals the mass times the acceleration in the x direction. And since this isn't accelerating in the x direction, there's zero acceleration, there's zero net force. But the sum of the forces in the x direction are just the adding up the force from the hinge in the x direction, this force right here, and the force in the x direction from the tension. So the tension in cosine theta, or the tension in the x direction. So if we add those up, we get zero. This one will make negative added to the other side. We just think about them as being balanced forces. So the forces to the right equal the forces to the left. We get zero net force from that. That means this force and this force balance each other out. So this would be the equation that I would make for that. In the y direction, we have something very similar. We've got two forces up, the force from the hinge, and the tension in the y direction, or t sine theta. We've got two forces down, the forces of gravity for the beam and for the sine, and those forces up have to equal those forces down. If they do, they're balanced and we have zero net force. So this is the equation that I would make for the y direction. And of course, there's different ways of writing this. We might add all these up together, and these would be negative forces, and then set them equal to zero. Or we can just write it like this. So this would be perfectly fine. In the torque equation, we have to deal with all the torques trying to spin this thing in the counterclockwise direction, and the torques trying to spin it in the clockwise direction. It turns out that if it's not spinning at all, not rotating at all, we can choose any point we want to be the point that we pick as a pivot point. I'm going to pick this hinge because that seems most natural. So from that hinge all the way over to this tension force, where that tension force is acting, they tell us the length of that beam is L, so that R in the equation RF sine theta, that's how we calculate our torques, that R would be this length L. The force would be the tension T, and of course the angle we're given as theta. And so we'd have RF sine theta would be LT sine theta. That's the only thing trying to spin it in the counterclockwise direction. So in the clockwise direction, we have two torques. One of them is going to be from the beam itself, and one of them is going to be from this sine. So the force from the sine is also a distance L away. So again, when we're doing the RF sine theta to calculate our torque, the R, the distance from the pivot to the force, is going to be L. The force is going to be the force of gravity. That's going to be the mass times gravity, or the mass of the sine times the gravity. And this angle right here is going to be 90 degrees, so we don't have to include that because that would just be 1. The force from the beam itself, okay, has a torque. Obviously, if we just let that beam go and it was hinged at this point, it would start rotating down. That torque is again going to be calculated with the RF sine theta equation. The R, the moment arm, now it's halfway to the end, so that's going to be L over 2. The force is going to be the force of gravity of the beam. And again, it's acting at 90 degrees, so we don't have to worry about that sine of the angle part of this equation. So we end up with this as our equation for the sum of the torques. And that is all we need.